Okay, so now I want you to compute this line integral. Compute the line integral of the vector field f over the curve c, where f is equal to this vector field. I didn't tell you what c is, but c is just going to be this circle of radius 1 centered at the origin. Okay, so how can we, we want to use Green's theorem to solve this problem. So let's think about how we can use Green's theorem. So remember that another notation for this f dotted with ds, remember another notation is just going to be equal to c xy cubed dx plus minus 3/4 x to the power 4 dy. Those two things just mean the same exact thing. That's what this thing here means when we have the dx and the dy. Okay, that was back when we talked about line integrals. Okay, so now we want to use Green's theorem to compute this, which is the same as that. So it's a circle of radius 1. So let's go back to look at what Green's theorem says. So by the way, this is at the bottom of these notes. So this is what Green's theorem says. So P is a thing that multiplies by x. P is a thing that is with the dx. So this is P. So P of xy is equal to xy cubed. The partial derivative of P with respect to y is equal to 3x y squared. Q of xy is a thing that multiplies the dy. This is minus 3/4 x to the power of 4. The derivative of q with respect to x is equal to minus 3 x cubed. And so now what does Green's theorem say? It says the line integral is equal to the double integral of qx minus py. So this is going to be the integral over the region R, where the boundary, so the curve is the circle of radius 1 centered at the origin. So then R is going to be the disk of radius 1 centered at the origin, and it's qx minus 3y. So this is minus 3x squared minus 3x y squared dA. We can factor out a minus 3. This is going to be the integral over R, and notice I can factor out, this is minus 3x cubed. I can factor out an x, and I get x squared plus y squared dA. Now this is a good candidate for polar coordinates, so we'll switch to polar integration. We're integrating over a disk of radius 1. So theta is going to go from 0 to 2 pi because we're integrating over the entire disk. R will go from 0 to 1. We'll go on ahead and write the r dr d theta. You don't want to forget about that. When you switch to polar coordinates, you don't want to forget about that. Now we'll convert the integrand to polar coordinates. The x is r cosine theta, and then the x squared plus y squared is, of course, r squared. And this is, I'm not going to do this integral. This is the integral theta equals 0 to 2 pi. R equals 0 to 1. Looks like r to the power of 4 cosine theta dr d theta. And that is an integral that you can do on your own. But again, this is just a Green's theorem problem.